Okay, so now Paul Ryan will continue this discussion about separation of variable.
Okay, thank you very much. And let me start by thanking the organizers for the invitation to come here. It's been a very nice conference for me so far and gave me the opportunity to actually meet many people that I've only ever discussed with by email before. So this has been nice. And it's always nice to come to France to talk about, well, in particular, correlation functions, especially since so much work was done here on this topic. So I'm going to more or less continue where Simon left off and speak about functional separation of variables and in particular about computing correlation functions within this framework. So this work is mostly based on two papers, one of which Simon mentioned and another one which is slightly earlier. And these works are in collaboration with these people. Simon Eckhammer, hopefully you know because he was speaking a few minutes ago. Nikolai Gromov, both of which are at King's College in London, and also Niccolò Primi, who was a PhD student in London and is now a postdoc in Turin. Okay, so I think most people will agree with me when I say that correlation functions are probably some of the most important observables in quantum systems. And so when I speak about correlation functions, I want to be maybe a bit generic. And what I mean is just going to be some matrix elements of some operators, okay, in the eigenbasis of conserved charges. So I have some, say, conserved charges with eigenvectors psi A and psi B, and I want to look at the overlap psi A with some operator O and psi B, okay? And this can be quite generic. For example, you can think of this O as being some product of local operators along the spin chain, or maybe in the integrable case, for example, some Yangian generator or quantum affine algebra generator or something like this, okay? I'm not going to right now specify what this means. I will leave this for a few moments. But at least in the context of quantum inverse scattering method and beta ansatz and all of these things, usually we have some quantum algebra hidden underneath everything we do, right? We have some R matrix, which satisfies Yang-Baxter equation, and we have some operator T, which satisfies RTT relation, and this T is generating for us this quantum algebra, okay? And usually in these types of models, the correlation functions which we're really interested in are these matrix elements of products of these monodromy matrices at different values of the spectral parameter. And why are we interested really in these? Well, on the one hand, these operators can be shown to generate all possible observables of the model, and also by using the inverse scattering transform, which we heard about in yesterday's talk, we can extract from these T's local operators at individual sites of the spin chain and really study physical correlation functions between different sizes and study how length changes and so on. Okay? So in the past couple of years, especially through beta ansatz methods, there has been really huge progress in computing these things and various related quantities. Especially, I think one of the main papers came out in 2012 or 2013, if I believe, which was on form factors in GL3, rational GL3 integral models, which allowed these correlation functions to be expressed in determinant form. And this determinant form of all of these observables seems to be a very recurring feature. And there was a very nice paper of Samuel and Nikita Slavnov from, I think, 2019, where really the determinant structure of these things was sort of, had a lot of light shed upon it and was related to the properties, structural properties of beta vectors. And these have also been extended to supersymmetric spin chains. And there has also been a lot of interest recently in related observables coming from this.
Can someone avoid the label on the top of the slide?
Maybe I can move it. This one? Okay. Okay. Yeah, so within this context of this modified algebraic beta ansatz, there has been interest in related quantities, for example, scalar products between beta vectors corresponding to different twists. Okay? And these scalar products between different twists can really be understood as a correlation function of an operator which changes the twist of one of the beta vectors. And actually, as we know from work related to quantum field theory, for example, with feather, we know that these overlaps with different twists are actually a very useful quantity in this context, because having a different twist acts as a sort of regulator when you are dealing with infinite dimensional models where you can encounter a divergent scalar product. Similarly, there has been some work on supersymmetric GLM/N spin chains, and a huge amount of work on computing boundary overlaps in this framework, in particular from the work of Balázs and Tomáš, who's written many papers on this subject. And of course, there are many results for related models, XYZ, boundaries, twisted Yangian, which Vidas is working on. So we have... Okay, now this doesn't work. Okay, so we have all of these nice results coming from beta ansatz. So this functional approach to separation of variables, which we've heard about in the last talk, how does this fit into the picture? Okay, if we have all of these results, why do we need this new thing, and what can it actually give us, which is a benefit? And for me, at least, there are two main motivations, one of which we've heard a lot about in the last talk, which is that these methods seem to be somehow useful when it comes to solving integrable quantum field theories. Okay, in particular, four-dimensional quantum field theory, n equals 4 super Yang-Mills. The reason being is that in n equals 4 super Yang-Mills, we don't have a notion of beta roots at finite coupling, so beta ansatz is not a really good concept, but we do have Q functions. Okay. In particular, all of these methods seem to work very well in infinite dimensional representations where there is no notion of a highest weight state. There's no vacuum. We cannot study excitations above a vacuum in a typical beta ansatz style. And also they work when there's no spin chain at all, if you just have Q functions. And for me, at least, actually, a motivation which I've become especially interested in maybe over the past year or so is related to the structural properties of quantum integrability. And what I mean by this is, classically, we of course know about the classical spectral curve, and of course there are many papers and books written on this, where the philosophy is that the classical spectral curve and classical Lax matrix encodes all dynamical information of the system. So you have the classical Lax matrix, you construct a classical spectral curve, you look at Pohl's dynamical divisor of eigenvectors of this Lax matrix, and this allows you to reconstruct all dynamical information of the model. So when we quantize, we can naturally ask, what is the quantum analog of this construction? And the classical spectral curve, when quantized, essentially becomes a quantum spectral curve, which is none other than the Baxter TQ equation. So we know that the Baxter TQ equation encodes all the spectrum of conserved quantities, and we can naturally ask, what other dynamical information can we extract from the Baxter equation? Can we, in a similar way to the classical spectral curve, use it to reconstruct all possible dynamical information of the system?
What is T cluster? T.
T?
Yeah.
Monodromy matrix.
The TQ relation is the equivalent of the spectral curve.
Yes.
So I'm wondering what is T classically? So in which sense the TQ is really the quantum version of the usual quantum of the usual of the divisor.
So when you say T, do you mean transfer matrix or monodromy? Classical transfer matrix, functions which are in involution. I
want to see it inside the first equation in your slide. Can I?
Yes, trace of classical Lax matrix, classical monodromy matrix.
Yeah, it's the first term of the expansion.
Yes, precisely. Yes. Integrals of motion are just spectral invariants of classical Lax matrix. Yes.
Although classically it doesn't look like the TQ system really.
Yes, there's no Q. Yes, Q arises as a quantization where this T, the notion of quantization is where classical matrix becomes replaced by something called quantum Manin matrix. This, by construction, necessarily involves introducing some shift operator. Shift operator has to act on something. This thing it acts on is Q function. This is how this would arise.
No, I do agree, yeah. Somehow, yeah.
Okay. So before I get into what other observables we can extract from this approach, let's just quickly remind ourselves what we saw in Simon's talk about this functional separation of variables. So the key object which we start with is this Baxter finite difference operator O. So we have this Q theta polynomial which encodes all of these spin chain inhomogeneities. Okay, so O is Q theta with U plus I over 2, and then a shift operator D, which shifts the arguments of my functions by plus minus I or I over 2, depending. And then we saw these brackets which were introduced, which were corresponded to integrating the function with some measure along some contour, some big circle, something like this, with the property that the Baxter operator is self-adjoint. This was the key property, that it can act on the left or the right and give the same result. And we saw that there were a family of such brackets, these F alphas, corresponding to these integrals picking up different poles in this measure when you do the integral by residues. Okay? And we also saw that this functional approach allowed us to write down a scalar product on the space of states just by writing down a determinant of integrals of these Q functions corresponding to the different states. Okay, this is the key philosophy within this functional approach that, and especially what we're going to see later, is that all observables, I think actually there's a, where's my punchline slide? Okay, this disappeared, okay. Yes, but okay, there's a slide missing, but we don't care too much. So main point is that observables will correspond somehow to determinants of integrals of Q functions. This is the main takeaway point, okay? So I'm going to sort of skip straight to the punchline and tell you what kind of objects we can compute. And I've decided to bring things into maybe a notation which is maybe more familiar for this community to relate to results which have been computed, for example, by beta-ansatz methods. So one thing we can compute is the overlap of transfer matrix eigenstates corresponding to a different twist. So for example, the overlap of psi tilde of some state A with psi B, where psi tilde, or psi, is an eigenstate of the transfer matrix built with either a twist G, which for example is diagonal, and another twist G tilde, which can be generic. And the only requirement is in fact that there is one constraint relating to these parameters, which is in fact very similar to your setup in beta-ansatz. So at least when we did all of this, there was a sort of underlying assumption that this second twist was diagonalizable. But based on experiments, I am quite sure that diagonalizability is not necessary. This can be allowed to have Jordan blocks, but we have not exactly explicitly checked this. And also that this should work with inhomogeneous TQ equation. And so to give you the example, so we know that this overlap of twist with different twists is going to take the form of a determinant in integrals of Q functions. And so for an example of a single site in SU2, we're dealing with a 1-by-1 determinant, no matter how many magnons we have, okay? So this is in contrast to beta-ansatz, where the size of the determinant is growing with the number of magnons. Here, for length 1, for example, for SU2, the size of the determinant is the length of the spin chain, not number of magnons. So if you wanted to, say, consider the scalar product with, say, 10 million magnons, you only need to compute one integral of a polynomial of degree 1 million, which is, okay, this is trivial. Okay, you do this in Mathematica. Okay. Next, we can take these results and start to put in insertions of monodromy matrices. Okay. So I've written some suggestive notation that TU of Z, which means some particular linear combination of monodromy matrix elements. And there are many different possible things which you can put in, and most importantly, you can put in enough monodromy matrices to generate all possible observables. You can generate the complete spin chain Yangian, for example, and also put in double insertions, triple insertions, and so on. Simon showed us how to use this functional approach to compute overlaps with integrable boundary states. In fact, we can go even further. We can compute overlaps with integrable boundary states and insertions of monodromy matrix elements. And also we can compute the overlap with a complete basis of integral boundary states B. Okay? And perhaps most importantly is that these formulas essentially go true for any rank GLN and for any highest weight representation. In fact, they also work for non-highest weight representations, but that's more less schematic and laid out, but we know the formulas work. Okay? So are there maybe questions at this point?
What do you mean when you can compute? Sorry, it was a large question. You can compute everything numerically, you put on the computer. You have a closed...
We have a closed analytic expression. Yes.
At some point, I guess you will show us...
Yes. I'll show you explicit examples for some maybe low number of sites or something, but yes, we have explicit closed expressions which you can write down analytically, yes.
In Mathematica?
No, I mean, physically I can write it. I mean, I can write down the formula on paper. It's I mean, if you want to compute something for a large number of sites, something like this, then of course, I mean, at some point you need to, paper becomes not very efficient. But closed analytic expression. When I say compute, I mean closed analytic expressions, okay? So to sort of explain how all of this works, I'll start with some simple example. And I apparently did not cite them. So this was initially done in a paper of Feather, Andrea Cavaglia, and Nikolai Gromov, which showed how from this functional approach you can compute diagonal form factors. And sort of the starting point comes from quantum mechanical perturbation theory. Okay, so if you remember this Hellman-Feynman theorem from elementary quantum mechanics, the idea is that suppose we have some eigenstate of a Hamiltonian with energy eigenvalue E on the left and on the right, and suppose this Hamiltonian depends on some parameter P. So in the spin chain case, this could be, well, any parameter you like. For example, it could be a twist parameter, an inhomogeneity, something like this. Or if you have, say, double row transfer matrix, it could be a left boundary parameter, a right boundary parameter, or something like this. And this theorem tells us that we can compute the derivative of the Hamiltonian, its expectation value, just by computing the derivative of the corresponding energy eigenvalue with respect to this parameter. So the point from this functional approach is actually that we do not need to compute the energy eigenvalue at its derivative. In fact, we can compute it at a fixed value of this parameter, which makes these formulas much nicer. So the starting point is a trivial relation, which is just that I take my Q function, I act with Baxter operator, I get 0. By definition, Baxter equation kills Q function. I put another Q function on the left, and I sandwich all of this inside this bracket, which I remind you is just one of these integrals which picks up some residues and so on. Okay, so this is 0 just because Baxter kills Q. And now I want to start shifting my parameter. So suppose I have twist or something fixed to some specific value, and now I want to shift it by some small amount. I want to change P to P plus delta P. So what happens is that all of these things, these Q functions and Baxter equation will also be changed. So for example, O will go to O plus delta O, Q will go to Q plus delta Q, and this will still be 0, right? Because I can shift some parameter, I can remain on shell, and everything is fine. And what you can actually show by using these bracket properties and so on is the following relation, is that actually Q times derivative of Baxter operator with respect to P times Q again inside this bracket gives me 0. Okay, this is really the key relation, because now I want to expand out my Baxter operator and separate the parts which are independent of state and the parts which do depend on the state. So I'm calling Y the parts which do not depend on the state. It's all of the sort of the source terms in the Baxter equation, this Q theta, and also the asymptotic part of the transfer matrix, which, as Simon told you, is independent of the state. And so when I compute these derivatives, this Y term, when I compute these derivatives, I'll have two parts. One will be derivative of Y, and the other will be derivative of my integrals of motion. And the derivatives of the integrals of motion are really the key things which I want to compute. Okay? So when we take this expression, plug in this, take derivative, what we end up getting is a inhomogeneous linear system for the derivatives of the integrals of motion, which, of course, in the usual linear algebra way is solvable by Cramer's rule. And so the expressions which we end up getting, for example, is that the derivatives of the integrals of motion can be expressed as a ratio of determinants. The determinant on the bottom is precisely the scalar product, and the determinant on top is the scalar product, but I start to replace columns by the inhomogeneous part of the linear system. So to give you a very concrete example, in the case of SU2 for two sites, I'm dealing with this type of determinant. And this notation, beta goes to this, means I replace column beta with the corresponding inhomogeneous part. So 1 goes to this, meaning I'm replacing the first column. 2 goes to this, means I'm replacing the second column. And then by inverting this quantum mechanical perturbation theory logic, this means we can write the expectation value of this non-trivial operator as a determinant in these Q functions. Okay? And this is sort of the main point. This is the main point which keeps coming up again and again, that the scalar product corresponds to some determinant of Q functions, and that operator insertions correspond to inserting different parts of the Baxter equation into different columns of this determinant. So there is somehow a mapping between, say, Yangian generators and different components of the Baxter equation, which allows you to write down these observables in a simple way. And yes, this is my punchline slide, which I actually thought came earlier, but it's what I've just said, that matrix elements will correspond to inserting different parts of the Baxter equation. So we can compute a lot of these different diagonal matrix elements just by taking derivatives with respect to some parameter. But what are these operators physically? If I give you, say, XXX spin chain with, say, L sides, and I tell you to take derivative with respect to some parameter, what is the actual operator that you're looking at? What have you computed? And you might think that it's some insane operator with no physical relevance, but actually in all cases we look at, these are actually very concrete operators with very nice physical properties. For example, if you take this parameter P to be a spin chain inhomogeneity, then the resulting operators or diagonal form factors that you compute are actually one-point functions of local spin operators. And these are very physical objects. Okay. And for example, if you go to something more exotic, like conformal fishnet theory in 4D, which just corresponds to an SL4 spin chain in principal series representations, which has a free parameter called coupling constant, then this actually corresponds to a 3-point correlation function of local operators in the field theory perspective. Okay, so these are really hands-on operators and not like nothing weird. When I first thought about the idea of, or like saw this, that you would compute operators by taking derivatives of some parameter, I expected these operators to be a bit not very hands-on, but in fact they are. But this is all well and good, but at the end of the day, these diagonal matrix elements are only part of the story, right? If we really want to say that we have solved a quantum system, we would like to be able to write down all possible matrix elements, off-diagonal matrix elements of a complete family of observables. And so the natural question is, can we extend this functional approach, these results which we got for diagonal form factors, is there any way we can easily upgrade them to off-diagonal correlation functions? And the answer is yes, provided that we take this parameter P to be one of the spin chain boundary twist parameters. And this is quite technical. I'm not going to get into the details of how or why this works. It comes down to what Simon mentioned, that in this particular base twist that he showed, that the spin chain SOV basis becomes independent of twist, and then sort of inverting this logic, it doesn't really matter. But at the end of the day, it turns out that when you take this parameter P to be a spin chain boundary twist parameter, all of the formulas I showed you in the previous few slides where I have determinant of Q functions with some insertions of Baxter equation can be upgraded to different states just by replacing the corresponding Q functions with Q functions of different states. So instead of, say, Q and Q, one Q function is now QA and the other Q function becomes QB. And this encodes all the state-dependent information. And in fact, even better is that these psi's don't even need to be, say, transfer matrix eigenstates. They can belong to a larger class of states, which in SOV literature are usually called factorizable states. And for example, you can also take these Q's to be not Q's corresponding to, say, beta ansatz equations with generic functions, which should somehow correspond to, normally I would say off-shell beta states, but I think in beta ansatz community there's more of a precise notion of what off-shell beta state is, so I don't want to make this super precise, but in any case, yes, states which do not satisfy beta ansatz equations. Okay, and also that what we can show is that these operators, given by taking all possible oh yeah, sorry, what I also forgot to say is that this elementary quantum mechanical perturbation theory usually works with a single derivative of this parameter. If you try and take more derivatives, then this approach fails. In fact, if you read Feynman-Hellman theorem on Wikipedia, it explains why it fails, and it's quite a common thing, and people try to generalize, but it doesn't work. But somehow what we observed, and of course we can prove that it works, is that we are able to insert any number of derivatives in twist parameters on these observables just by taking more and more derivatives with respect to twist of the Baxter equation. And by taking all possible derivatives in twist, we are in fact able to generate the full algebra of observables. So we can generate the full spin chain Yangian in this way. Okay, so this was sort of for SU2, spin 1/2 spin chain, but suppose I wanted to extend to a more general representation. So suppose I wanted to go to, say, some non-compact, say, spin -1/2 representation or something like this, or generic spin representation, then it's very simple. All of the representation details are encoded in this measure, this integral which we perform, which picked up residues. And in fact, if you want to change representation, all you need to do is to change this measure a bit to now contain an infinite number of poles and change the contour a bit. Okay? And similarly, if you do SLN, you can go to more generic representations in the same way. So the formulas do not change. Okay? The formulas as written as integrals do not change. All of the representation-dependent information is here in this measure. And as Simon explained, these formulas for scalar products extend in a more or less obvious way to, or a more or less clear way, to higher rank. The only difference is now that there are more Q functions with more indices. Okay? So we saw that the scalar product depends now on, say, Q's, say Q and some Q's, some upper indices with some now extra shift operators. Okay? But actually all of these expressions for these form factors, these derivatives with respect to twist parameters can also be computed in the same way, just by taking the scalar product and inserting some parts of the Baxter equation. Okay, so in the last 10 minutes or so, or maybe a little bit less, I want to mention about the extension of this to correlation functions with integrable boundary states. And I'm not going to get into details, I'm just going to sort of sketch the results. But the main point from what we saw from at the end of Simon's talk was that there is this special singlet integral boundary state, which we denote by W. And we saw that its overlap with a transfer matrix eigenstate can be written as a determinant, again, of integrals of Q functions. And so we can ask what other types of observables will admit such a representation. Can we sandwich some operator O between, say, W and psi? And of course, perhaps the most obvious thing we could do would be to insert the transfer matrix. Why insert the transfer matrix? Because the transfer matrix will act on psi, it will produce its eigenvalue, and then we're just left to compute the overlap of W with psi, which we already know. Okay? And what is actually interesting is that this action by transfer matrices actually generates all possible integral boundary states. And there, for some reason, again, I think similar to what happened to Simon, is that my citations are not showing up. There was a citation here to a paper of Balash where this idea was exploited quite explicitly in various integral models, using the fact that, for example, if you start with something like a matrix product state, you can act with transfer matrices and so on to generate more and more integrable boundary states. So this idea is not new, it was already in a paper of Balash and collaborators. So we can then look at something more exotic. For example, we can insert, say, some monodromy matrix elements within the integrable boundary state and the transfer matrix eigenstate. And it turns out that this is essentially exactly the same as before. All that is happening again is that we take the formula Simon showed for the integral boundary overlap and we insert parts of the Baxter equation and act on these different Q functions. Okay? It's exactly the same story. Okay, so I'm about 5 minutes early, I think, but I think I can start to finish up. So I'll just mention some conclusions and what can be done in future. So the key point I want you to take away from this is that matrix elements of observables correspond to inserting the Baxter equation in these determinants of Q functions. Okay, that is like the main point. And different operators correspond to different parts of the Baxter equation, right? The shift operators in different directions, the diagonal part with no shift, these correspond to different, say, Yangian operators. And perhaps most importantly is that these types of formulas and this methodology works for any rank and representation. And so to mention some future directions, so as Simon said, one sort of key thing which is yet to be properly understood is how to generalize these methods to supersymmetric spin chains, say based on SL m/n. And once this is understood, say in the rational spin chain point of view, one could extend to the Hubbard model. And the Hubbard model for me would be especially interesting because it would serve as an excellent testing ground for this 4D quantum field theory example, due to the fact that the Hubbard model at finite temperature can be viewed as a sort of testing ground for n=4 super Yang-Mills. They have very similar analytic properties, just fewer Q functions, and so it's sort of a bit more tractable. The other natural thing to do would be to generalize these methods to other algebras, say SO2R, which have been extensively studied recently. And another thing which I think would be interesting to many of the people here would be to study these types of methods when we deal with open boundary conditions, for example, twisted Yangian or reflection algebra or something like this. And one of the main motivations, at least for me, for this is that these twisted Yangians, so in the same way that rational spin chains and periodic spin chains correspond to single trace local operators in n equals 4 super Yang mills, these twisted Yangians correspond, in fact, to Wilson loops, which are another very interesting class of observables. So there's certainly a lot to do. And if people are interested in discussing any of these things with either me or Simon or both, please do let us know. And I will stop there. So thank you very much.
Okay, any question?
I have a question about the statement that the action of the transfer matrices generates all boundary states. It's so you have a proof, or
yes, proof. Yes. Mm-hmm.
It's interesting because the boundary states are representation of twisted Yangians. Mm-hmm. So twisted Yangians has a Lie algebra, algebra, and also the transfer matrix also corresponds to some representation of the original Yangian. Mm-hmm. So, for example, in the SU3 case, there is a situation when the twisted Yangian has SO3 symmetry and the Yangian has SU3 symmetry. And so I'm wondering how the action of the transfer matrix generates all boundary states, because the boundary states corresponds to SO4 representation, mm-hmm. and the transfer matrix corresponds to the SU3 representation. Yeah, so it means that you can generate all the SO3 representation from the SU3 representations, and it's something weird statement.
So I am not claiming this, and what I am claiming is that. So I think the key point which separates what I'm saying from what you're suggesting is the fact that I'm working with the twisted spin chain. Mm-hmm. Okay, so the statement is that by acting with transfer matrices on this singlet state, we generate all integral boundary states for the twisted transfer matrix. Okay, and we can explicitly compute all of them. For example, for length for two sites, I think there are precisely 3 integral boundary states which we construct, but we can see explicitly that as soon as there are integral boundary states for the untwisted chain, which are not integral boundary states for the twisted chain. Like, for example, matrix product state. We do not construct matrix product states by acting on the singlet state with transfer matrix, precisely because matrix product states are not integral boundary states for the twisted chain. And I am suspecting that that is sort of the answer, that these class of integral boundary states which you were speaking about are not integral boundary states for the twisted chain. This would be what I would suspect, because we have a precise, this construction we have of building states by acting with transfer matrices was inspired by the Maillet-Nicolai story of constructing an SOV basis. You start from some reference state, act with transfer matrices, and then you check based on, say, looking at the transfer matrix in the large inhomogeneous limit, that it becomes some very simple local acting matrix. You check that its determinant is non-zero, you know that you have a complete family of states. This was the logic. So yeah, I think the answer is that these states you're referring to are not integral for the twisted chain.
But this also means that, so in the physical applications, for example, for the one-point functions, this matrix product state is relevant and appeared, and your method can be
to be determined. So in fact, this is one of the reasons why we're so interested in the fact that we can compute these insertions. It may be possible to construct matrix product states by acting on this singlet state with certain action of monodromy matrices, which we can compute the overlap for. We didn't do an extensive analysis to see if we could construct matrix product states in this way, but it's something which can be checked.
Okay, thank you.
So Paul, may I ask a question? If the size of the spin chain go infinity, you found that it's easy to take the limit of this kind of limit?
At the moment, it is not clear how to take this limit. So these determinants we have will depend on the length, precisely depend on the length of the spin chain. So now we are dealing with some infinite by infinite determinant, and the precise meaning of this for us at the moment is not clear. There are expectations. For example, these formulas which we have are very similar to one-point functions in, say, Sinch-Gordon model, which were written down by Lukyanov. And then it is known that these types of determinants should become some type of Fredholm determinant. Mm-hmm. What exactly happens in our case and how to rigorously take that limit is not clear yet.
Thank you.
Okay, so maybe we can thank the speaker. Thank you very much for here.